So for example, let's actually introduce an example of like a pretty well-known case of a high-resolution scheme, right? Something that works pretty well. That also represent something that's a little bit different from the kind of finite difference schemes we have talked about. The scheme is trying to approximate du dx at xi as a linear combination of ui plus 1, ui, and ui minus 1. Okay, this is pretty standard. But I also represent it as a function of u prime I minus 1 and u prime I plus 1, where u prime I minus 1 and u prime I plus 1 is just the first order derivative of the same function at I plus 1 and I minus 1. Now that's interesting. The first question is, how do I actually use that scheme? We actually now start to have a numerical scheme which we want to approximate the first order derivative, but actually to evaluate the scheme, I have to know the first order derivative to start with, right? Isn't that circular? Anybody wants to take a stab on, like, is this a completely pointless scheme that there is no way for me to actually use it? Because this is actually the derivative at xi minus 1. This is the derivative at xi plus 1, right? Have we seen something like this before? It's like implicit time stepping, right? It's like implicit time stepping, where in order to evaluate the solution at the next time step, I have to evaluate the right-hand side on the solution at the next time step. So this is actually so-called an implicit, right, approximation. And just as the way you evaluate an implicit time stepping scheme, can you think of how you would actually use this finite difference approximation? If I figured out what the values of A, B, C, D, and E are, right, how do I use this?
You can form a system of equations.
Exactly. What I do is I can form a system of linear equations with the unknowns being the derivative of the finite difference approximation derivative at every grid point. And then I can solve them. It's simply by moving the D and E terms to the left-hand side, right? And then we get a bunch of coupled equations, and I solve the matrix system with the coefficients. Basically, with the tridiagonal system, with the tridiagonal components are D, 1, and E, right? Okay, so that's how I can evaluate the finite difference scheme. Now we know that the scheme can be actually evaluated. Let's figure out what A, B, C, D, E should be. Again, we use Taylor series, right? So ui plus 1 is equal to ui plus delta x u prime. I mean, all the regular stuff. Let's maybe not even have to write it down. I don't know. So 1, 2, 3, 4, and 5 terms. Because we have 5 unknowns, we should have 5 terms, right? And similarly to ui minus 1, and I won't just write it down, the coefficients are similar, but then ui plus 1 prime is different. This term is 0, all right? And this term actually is just a ui prime. I'm actually expanding the first order derivative. Now this term actually corresponds to delta x times ui double prime. Right? So basically, I'm just taking a Taylor series expansion and take derivative on every term. It just results in every term gets shifted towards the right. I mean, towards your right by one term. Right? So this is like here. This is like here. And the next term is half of delta x squared times u third order derivative. And then I have delta x cubed fourth order derivative. I minus 1 is the same, ui prime minus plus and minus. Right? And finally, I have ui equal to ui. So let's plug in these 5 terms into MATLAB and figure out what the coefficients should be. So actually, let's have the terms to be right. So this is A, this is B, this is C, and D, and which is D, which is E. Okay, this is D, this is E. Okay, so let's follow the order. So the matrix A is the first line is 1 1. Come on. Okay, 1 1 half, a sixth, 1 24th. The second line is the value corresponding to minus delta x is 1 minus 1 a half minus 1 sixth and 1 over 24th. Actually, sorry, the second line is corresponding to ui, I think. Yeah, B is actually ui. So the second line is 1 0 0 0 0. And third line is this. And the fourth line is, let's see, it starts to be the derivatives. It's 0 1 minus 1 half and minus 6. So 0 1 minus 1 half minus 1 sixth. Last line is the same as the second last line, but have all plus signs. Okay, so that's my matrix. And I want to the transpose of the matrix A backslash with 0 1 0 0 0. That's my coefficients. Okay, so the scheme turns out to be ui plus 1 minus ui divided by delta x times what? 3 over 4, and then plus, actually minus a fourth of ui plus 1 prime plus ui minus 1 prime. Okay, so that's ui prime is approximated by this. Oh yeah, ui minus 1. Yeah, thank you. Yes, because the B term turned out to be 0, right? Okay, so what do you think is the order of this finite difference scheme? What's the order of accuracy? Yes, it's actually fourth order accurate, because if you expand one additional term, that additional term is going to be proportional to delta x to the fourth, right? Or if you expand one more term on the values as opposed to the derivatives, it's going to be divided by delta x. It's also delta x to the fourth. So O delta x to the fourth. All right.